general. And I just want to very briefly give a concise summary of the field theory side of the specific duality, the n equals 4, d equals 4 to ADS5 cross S5 duality that we're focusing on as a prototype. So the action is, one can concisely write the action down using dimensional reduction. So first start with d equals 10. And then the gauge fields, of course, and the fermions are matrices. Everybody's an adjoint when you have coincident d-branes. So you just write down pretty much the simplest thing you can. Oops, that's a chi. And that is a Yang-Mills action and an action for the, for a fermion, and I'll tell you what kind of fermion in a second. And this is just a Dirac action and a gauge action, but it happens to have supersymmetry. It has one 10-dimensional supersymmetry. But now to get to the theory we're interested in, we just dimensionally reduce. So we split xm into x mu for mu equals 0 through 3, and xm for m equals 4 up to 9. And so d10x just becomes, we just ignore the dependence of the fields on these 6 coordinates we don't want. So this becomes d4x. And of course, derivatives with respect to these then just are 0. They mean nothing. And you have your 10-dimensional vector potential, which separates then into a 4-dimensional vector potential. And 6 scalars from the dimensional reduction of A. So down in 4 dimensions, it looks like you have more fields and more terms in the action, but they all descend from the Yang-Mills field strength. And you see right away that there was the original larger Lorentz invariance of the 10-dimensional theory, and we still have kept the 6th dimension we've ignored. We've ignored them all equally, so there's still an SO6 symmetry, which acts on the 6 scalars. Similarly, the fermions, they're the smallest spinner you can have up in 10 dimensions, 16 real components. That's Majoron or Weil. And if you similarly decompose these in terms of 4-dimensional spinners, they become 4 times a d equals 4 Weil spinner. In particular, these transform as a spinner representation of this. Okay. So that's pretty much all one needs. Just pretty much the field content, the symmetries. It's often useful, though, to think about the whole action in another way, which is starting down in 4 dimensions. If we have reason to, it's sometimes useful to focus on one. So the supersymmetry. The supersymmetry similarly is 16 real, which in 4 dimensions is 4 Weil spinners. So that's why it's d equals 4, n equals 4. Anyway, down in 4 dimensions, there's again another nice concise way to write the theory. If you focus on superfields that display one of the 4 supersymmetries, then so down in d equals 4, n equals 4, any one supersymmetry notation, you have a vector multiplet. You have 3 chiral multiplets, all in the adjoint. And of course, the four spinners, one lives in each of the chiral multiplets, the fourth lives in the vector multiplet, and it's because we are not showing all the symmetry that they're split in this way. And then it's just the standard supersymmetric action with a superpotential, which is of the form trace. So, okay, there are three. The chiral superfields, call them phi 1, 2, 3, trace of phi 1, commutator of phi 2 with phi 3. So it's just an innocuous seeming n equals 1 field theory with a particular kind of funny superpotential. But in fact, well, if you expanded this out in components, you would say, hey, I actually have this SO6 symmetry, and it's going to mix up the supersymmetry that's obvious in this description with three more that are not obvious. And this is useful because often one is interested in perturbing the theory in a way that in the end you only have one supersymmetry. Okay. The other thing about the field theory side, of course, is the n counting, the planar counting. So let me in Tufts large n limit, the thing you hold is fixed is G Yang squared n, also known as lambda. And so the whole action has an n in front. Actually, the whole action is proportional to n squared because there's an n here and an n hidden in the trace. But because there's an n in front, so now we're talking about just how things depend on n. At fixed lambda, each propagator has a 1 over n. Each vertex coming out of the span of the action has an n. And when you use the double line notation for an adjoint, there's an n for each index loop. Also, there are the things you're observing, and the things we're measuring, the things whose expectation values that we're counting will pretty much always be, well, most of the time, be traces of products of adjoints. So the operators we look at are things like traces that have some, a sub m's and a sub, well, f sub mu nu's and chi's and so on. But I'm going to make a convention for my lectures. I don't think this is standard, but as long as I tell you what my convention is, you're ahead of the game. That when I talk about the operator, I'm going to put an n in there. And that way they scale the same way as the vertices. So something like this would look like a vertex, 3 fields, and the trace, connects their indices in this way, and then there's an n just as there is for a vertex. And so with this counting, any Feynman graph goes as n to the number of vertices, where vertices include these operators on an equal footing, plus loops minus propagators, which, as Tufts remarkably noted, is just the Euler number of the graph when you fill in the index loops. And so you get a topological expansion based on the topology of the graph. So just for the 1 point, so if I have a single, suppose I just have a single phi squared operator. So here's the operator, 2 fields. The simplest graph would be just connect the 2 fields this way. And there's 2 n's from the index loops, an n from the vertex here, the operator, and a 1 over n for the propagators. This goes as n squared. And indeed, this is when you fill in this index loop. And this index loop is topologically a sphere. It's topologically a sphere, which has Euler number 2. For a 2-point function, you can do 2 things. So again, and if you if you dress this up with more propagators, you can do the counting for as many examples as you want. But Tufts' argument tells you that you'll always get n squared for anything like that. with two operators, there's two things you can do. You can either have the disconnected graphs, of which this would be the simplest, or you could have the connected graph. And when you fill in the index loops, this is two spheres, two disconnected spheres, which gives you n to the fourth. This is a single sphere, which gives you n squared. And the general rule with the conventions I've adopted is that so this is connected, the connected expectation value of any number of invariant operators will always scale as n squared, because it's always top. The leading contribution, the leading spherical, also known as planar if you flatten the sphere out, the leading spherical contribution to any correlator of any number of gauge invariant operators will scale as n squared. But the largest term will always be the most disconnected one, the product of the one-point functions. Okay, so that's the lightning summary of the field theory side of this particular duality. So now the main subject area, of course, is to bring these two sides together. First, the parameters. Let me just. One more thing I should say. The field theory, of course, the reason it plays a special role is that it's conformally invariant, it's scale invariant. If you just write out the beta function, the one-loop beta function, from this collection of fields, the matter exactly cancels the gauge field. The one-loop beta function vanishes, and in fact, the beta function vanishes to all orders and even non-perturbatively. There's a simple Seibergian argument for that, which I'll give you actually later on when it's more convenient to. Yeah. So good. So the theory has the SO6 symmetry, the Lorentz symmetries. It has the translation invariance, and it has scale invariance, and the rest of the conformal group. Good. Okay, so first parameters. We've already noticed, I think, earlier on that on the ADS side and the CFT side, we have n and n, and we have G Yang-Mills squared, and we have G string. Although it might be okay. There's another way to characterize this on the ADS side, which is if you go back through the definitions, the ratio of the ADS scale to the string scale, where the string scale is just the square root of alpha prime, is just exactly lambda, G squared n. And the ratio of the ADS scale to the Planck scale is essentially n. There's a number here that depends on your convention for what the Planck scale is, but it's essentially n. So, coming back to the hand-waving derivation, we need many fields, and we need strong coupling. And strong coupling, again, not just means of order 1, it means much bigger than 1, so that the strings are much smaller than the ADS space, and we can use supergravity. And similarly, this has to be much larger than 1, so that quantum gravity loops are small. The duality should still be true in the case that this is of order 1, and the ADS scale is of order the string scale, and we should be able to use some clever solvable string background to talk about this, but there aren't, partly because of the Ramon fields that come up in a lot of examples, there's, I think, not a lot that's been said about examples of this when this is of order 1. Okay, so there's the matching of parameters, and the symmetries. Again, SO42 cross SO6, the obvious geometric symmetries on the ADS side and on the CFT side. We've just seen this one, and we talked about how the various pieces of the conformal group of the Poincare coordinates fits into that. So those symmetries are the same. There's also the supersymmetries, which are the same. So this whole thing fits into a supergroup that I'm not going to try to describe. There are actually 32 of them. There are the 16 that we just talked about up above, and there are 16 superconformal. There's another symmetry which may not come up again, but it's worth remembering that it's there, since it is a symmetry, which is there's the SL2R on both sides. This is the weak-strong. So in the 2B string theory, this includes the weak-strong duality, the string duality, and also shifts of the Ramon-Ramon scalar, discrete shifts. And in the CFT, again, it's the weak-strong. This weak-strong duality of the 2B theory descends to the conformal, to the gauge theory, to the D3 branes, and again, it's weak-strong and shifts to the discrete shifts of the theta parameter. I mean Z. Thank you. Discrete shifts of the theta parameter. It's too early in the morning. Okay. So the next thing is to talk about the matching of the states. Now, of course, we're going to look at the map between the states on the ADS side and the states on the CFT side. But we know from general principles of ADS CFT that we can also, these are isomorphic to the operators of the CFT. And so the dictionary is, more concisely stated in terms of the operators, the local operators of the CFT and the ADS states. In particular, again, the single trace operators. So I could have also written something that had a product of two traces, but I didn't. So the single trace operators map to the one particle states. And that is kind of obvious from the point of view of this statement about how connected amplitudes are smaller, namely in the large n limit. In the large n limit on the CFT side, things factorize as much as possible into single trace, exponentialized single trace operators. On the ADS side, that same limit is turning off the bulk coupling constants, and so you have weakly coupled particles. Pardon? So if I wanted to count if I wanted to count the states, I would probably actually want to do it in the global picture, because there I get a discrete spectrum, and it's usually easier to count. So if I wanted to sort of phrase it in this way, I would go to the global picture, where ADS is, roughly speaking, a cylinder. The ADS is, as Itza put it, the soup, and the CFT is sort of the can. It's the boundary, the three-sphere on the outside, and then quantize on the three-sphere, which is isomorphic to these operators, and then compare it to the states here. And in fact, I put in the notes. Actually, so I guess by tomorrow I'll try to give you an updated notes. I put in the notes one small exercise to, in fact, do a calculation in this language rather than directly. But I'm going to simply use this as motivation to make the statement that the dictionary in the end is between actually particles. So it's between the different kinds of single trace operators and the particle species in ADS5. And you can state it in terms of not the particles themselves, but the field operators. So you have some field. I'll keep writing scalar fields just because they're simplest. And again, as we just discussed last time, we're going to quantize these in such a way that the quantum fluctuations, the actual dynamical field, behaves as z to the delta near the boundary, where delta is one of the two roots of m squared equals delta minus d. And we have some freedom as to which route we take in some cases, but whichever route we take, the field has some definite, the quantum part of the field has some definite fall up at the boundary. And so if we scale that out, so I like to think of this as the basic statement of the dictionary. That is, it's a statement that relates operators to operators. And if you think about it, if you come back to the original hand-waving interpretation of the z-coordinate, in terms of the size of the state you're making, a local operator at a point, is creating whatever it creates all on top of each other. It's creating some state of zero size. And so in terms of the dual picture, it should be creating something at z equals 0 as it is. This identity also sort of suggests, we always think in terms of the CFT living on the boundary of the ADS space. So if the ADS space is the global space, the CFT, again, is this three-sphere times time. If it's the Poincare space, which I guess Eva Silverstein draws it something like this, that is, this is a Poincare slice, and this is the throat conveying the fact that these directions are shrinking down as you go down to this. This is the boundary. This is the horizon. The CFT, the local operators of the CFT live here on the boundary of the space. I'm not sure. It's weird because, in a sense, I mean, remember this is an isomorphism of two theories. The CFT, the CFT is the entire gravity theory. It's a complete isomorphism of this theory and this theory. It's not so it doesn't sort of live just on the boundary, but all of the local observables and pretty much all the observables that we know how to write down live at the boundary. So it's in a sense, the CFT lives in the boundary of the space, but you have to remember that it really is constructing the entire theory in the interior. It might also bother you when you start to think about it that when we derived this in the brainy construction, all of the D branes were sitting down here at r equals 0, the horizon. and somehow they've migrated out to here, the other end. And one way to think about this is that these are, again, their positions are quantized. They're fluctuating all the time. And roughly speaking, it's the quantum fluctuations of the original D3 branes that you put at the origin are really building the entire space. And in fact, if you have a scalar field with like the position of a D brane, and you try to measure it very precisely, you measure it very quickly over a very small volume, you know by principles of quantum field theory that it will fluctuate over an arbitrarily long distance. And so as you make more and more local observations on the D3 brane, you're actually going to see things that are further and further away from where you thought they were. So in some sense, you can imagine how the quantum fluctuations of the D3 branes build the whole space. Okay, so we can check real quickly that with this dictionary, the conformal symmetries match up on the two sides. And again, there's in the CFT there is some list of operators. In the gravity theory, this again is all in 5 dimensions now. You have the 5 sphere. You know, when the hand waving derivation didn't know that we were also going to find a 5 sphere. I guess we had to because we had to get string theory. But it's different from the ADS directions because the Poincare directions are blowing up as you go to infinity. They feel the warping, and so they have these special kinetic properties. The 5 sphere just remains at some at constant size as you move out. It doesn't warp in this way, and so in some sense you can just reduce in harmonics in the 5 sphere and think of these as just different fields in 5 dimensions. So we can check that this dictionary has the correct conformal properties, that this delta that appeared in the solution to the Klein-Gordon equation really is the scaling dimension of the operator. So the scale symmetry, in terms of the Klein-Gordon fields, they're just scalars. The scale symmetry is just a symmetry of space-time. It just moves the points. Yes, question?
I didn't understand the point that you made about the CFT living on the boundary. I mean, what you said
well, it's geometrically the space that the CFT lives on is the same as the boundary of the ADS space. And again, that shows up very directly in the statement that the local operators in the CFT relate to the boundary limits of the fields. But then I was also saying, but we've got to remember the CFT is dual to the whole space. So, you know, it's not a sharp point I'm making. It's just.
No, how does it reconcile the fact that, as you said, the brain was on the other side?
Well, again, the brains, in the classical solution, the brains were on the other side. But if you actually sort of try to quantify how much they would fluctuate as a quantum object, it's essentially just enough to build the ADS space. So they're everywhere.
But then why z equals 0 is the limit that we need to take?
Z equals 0 is the limit we need to take. Well, two reasons. One is, in a theory of quantum gravity, it's very hard to make sharp observables. And the boundary conditions are such that the larger component of the Klein-Gordon field, or for the metric, the larger component of the metric, is fixed at the boundary. And so at the boundaries, you know, it's hard to pin down the metric. But because of this warp factor, the metric behaves, in some sense, more and more classically as you go out to the boundary. And so at the boundary, you have a place where you can sit and define precise observables. So in some sense, the boundary is where the boundary is the natural place to define observables in this theory, and it also again fits with this hand-waving interpretation of what Z is. If you could, well, if you tried to make an operator that created a particle somewhere in the middle of ADS space, which lots of people have tried to do, you can do it in free field theory just using the symmetries. But if you try to make an operator, you run into all sorts of complications and problems, and it's not clear what the precise thing is that you're trying to do, because you don't have local operators in general relativity. You can't, in some sense, create something that has energy at a point in a gravitating theory, because you have to also create its effect on the gravitational field. Question?
Yeah, so I was just trying to understand the statement about single trace operators correspond to one particle states.
Yeah.
So generically, if you take the trace of a product of phi's, you get some. You say in free field theory, you'll have a dagger times a dagger times a dagger.
Mm-hmm.
So is what you're saying that somehow in the large n limit, only the ones with a single a dagger acting in the vacuum are
No, I did not. No, sorry, no, I did not say that. I didn't say that. I said it's the single particles in the single particle states in the gravity picture mapped to the single trace operator. So it again fits with this hand waving picture that the entire cloud of things that this operator creates is a single particle on this side.
But a multitrace operator isn't?
A multitrace operator is two particles. A multitrace operator is two particles. And one way to see that in some sense is that this counting tells you that to leading order it has two pieces that don't communicate with each other. I don't know if there's a cleaner way there must be a cleaner way to say it, but if you act with a multi-trace operator, to leading order it's going to act like you've just acted with a single trace operator twice. And so it acts like a two-particle state. Yeah, Tom. Good question. Good. So for M theory, now, it's a really good question. Right. So just to expand on, there are, as we go around the landscape of string theory, we get to theories that don't have strings, like M theory, at strong coupling, and there are ADS-CFT duals involving M theory, and in those duals, the CFT side doesn't have a nice planar expansion like this, and you get funny and non-Tuftian powers of n. Now, you've thought about this more than I have, so
I don't have an answer.
Yeah. You have the obvious harmonics on this. I mean, you have the graviton, you have the obvious supergravity states, and then you have what, black holes. I mean, the thing of good. So
What I don't know how to do is talk about it to graviton state.
Well, we should think about this offline, because yeah. I don't have anything new to say. Yeah. So I mean, but it's true. The fact that there are these two scales, the string scale and the Planck scale, is special to string vacua, and it's sort of special to the fact that this field theory has a coupling that you can tune. Whereas in some sense, the dual to M theory is stuck at lambda equals infinity. It's stuck at, and so it's sort of the same story but less, at least in terms of the parameters. And in terms of the operators, it's a good question. Does this theory have operators that create black hole states? It does, right? We're not going to talk. Right. Yeah. We don't talk about that. Okay. Oh, good. There should be. Do they have to be stable? I mean, we don't. So we sort of kind of the strings. Well,
If you believe in the state operator correspondence.
it has to be true. Has to be true.
Black holes are like mixed states somehow.
Well, they have many individual. They're not. They have many individual states.
If you want to hear Conway's sort of tentative answer, it's that if you look from the free field theory point of view, you want to find states that behave thermally like black holes do. You have to look at the part of the spectrum that scales like order n squared.
Okay. Good.
Way up there, the degeneracies and
Good.
large.
Right.
And if you go to first order perturbation theory, it looks like you're going to get a random Hamiltonian purple states.
Very good. Good. So good. This becomes so large numbers of very large numbers of fields in the trace where the n counting begins to look non-standard. Right. Very good. Okay. Good. So if you just take the way a scale transformation acts on a scalar field in the bulk and you plug it into that dictionary, you find that this takes O of x to lim z goes to 0, z to the minus delta, phi of lambda z, lambda x, which by renaming the dummy index z is lambda to the delta, lim z to the minus delta, phi of z lambda x, which is lambda to the delta O of lambda x. So in this middle step, we've taken z to z over lambda. Just that's a dummy index. And so indeed, the operators defined in this way scale as they should under scale transformations. And in particular, the exponent that we got from the limiting behavior of the Klein-Gordon equation really is the dimension of the corresponding operator. Okay. By the way, these scalings, later on I'll do one calculation with gravitons, but these scalings work the same way. I think this is always true if you refer things to tangent space indices. So instead of g mu nu, instead of, say, the fluctuations of g mu nu, you sort of have to go to local inertial indices, and then the scalings of that thing, or of one of the fluxes, one of the forms that again, the scalings of these all scale the same way as the Klein-Gordon fields. The relation between the scaling of the supergravity fields and the scaling of the dual operators works the same way. Yes?
Do you think those bulk fields, I mean, is this a mnemonic, or are you claiming that phi of z and x is actually an operator on some filtered space?
Well, this is a good question. This is a good question because, and it's something which I've never had a good answer to, because the other way to state the dictionary, which I'm going to treat as a derived thing, still refers to bulk fields. It says the bulk theory is a path integral, and the dictionary has to do with the boundary conditions for those fields. So it's true that this way of stating the dictionary somehow, well, it's fine for the supergravity fields. It's probably fine for the string states if you work with them in perturbation theory. But it's a good set question because you say conceptually, when we get into parts of the, well, when we get into regimes where maybe quantum gravity is strong in the bulk or string effects are strong, you say we don't have fields necessarily. That's true. It's not clear what we have. It's not clear what you would build a dictionary out of. So I agree that this bothers me. It bothers me that this is all expressed in terms of fields in the bulk, and we don't know that fundamentally the bulk theory can be expressed as a field theory. Yeah, and it comes down to the fact that we don't know what the bulk theory is, except in limits where, like this one. So, yeah. Well, the question was, I'm phrasing the dictionary, and other ways to phrase the dictionary make reference to fields in the bulk. And this is a little bit embarrassing because the bulk A is string theory, so am I really sort of secretly trotting out string field theory? No, I'm not doing that. I'm just taking advantage of the fact that L over L string is a large number, and so I can at least describe the supergravity fields in low energy effective field theory, which is effectively what I'm doing here. Yeah. Why not string field? That's a good title for a paper. It's the right tool for some purposes, and it might in fact be the right tool for this one. I mean, modulo the technical annoyances of the Ramon fields. I think actually it's the right. I'm not sure that string field theory makes sense non-perturbatively, especially closed string field theory. On the other hand, it's sort of the nicest way to try. If you try to understand the divergences of string perturbation theory, it's kind of the nicest way to organize the diagrams. And as a practical tool, it might be the right tool here. I can't think of really much that's been done with the stringy states, and other than calculate the anomalous dimension of the Konishi operator. I mean, there's just not much been done. I guess maybe for the ADS3 duality that has only Neveu-Schwarz fields, a bit more has been done, without having to use string field theory. They're actually I haven't studied this in a long time, but there, I guess, the dictionary for the stringy fields is somehow couched in terms of the behavior of the vertex operators near the boundary. I'd have to think about how that works exactly, but Aguri and Maldacena, I guess, worked out some of the dictionary. Okay. So, there's a list of examples. So, the other thing about the mass-dimension relation. So, as we've just been talking about, there's two sort of obvious kinds of states in the bulk. There are states which were massless in 10 dimensions. So first of all, there are states which were massless in 10 dimensions, the supergravity states. And when you put them in ADS-CFT and you sort of interpret them in 5-dimensional terms, they'll have masses from their momenta along the 5 sphere and maybe from their couplings to curvature, but the scale of all of these things is the ADS radius itself. Tom got tired of reminding me that whenever I write this formula, it's m squared L squared. The fields which are massless in 10 dimensions only get mass from the sort of the curvature, essentially, of the ADS space in the S5, have masses of order 1 over L in D equals 5, so the Kaluza-Klein states, which means that delta is of order 1, whereas excited string states have masses of order 1 over the string scale, and so delta is then of order L over L string, which is the Tooth parameter to the quarter. And so this is a, well, striking prediction of the duality that there are two classes of states, some of which whose anomalous dimensions remain small, and some of whose anomalous dimensions become very large as you make the coupling large. Now, in this particular theory, there's enough supersymmetry that not only do these states have dimensions of order 1, but actually in the n equals 4 in the n equals 4 theory, the ADS5 theory we're talking about, delta for these is actually independent of G, independent of lambda. That is, not only does the dimension remain of order 1 at strong coupling, it doesn't change. So at low energy, it's of order 1 because it's just some counting of the dimensions of whatever fields appear in the operator. At strong coupling, it's still of order 1. It's the same number. And the argument, the argument is given in, for example, Witten's original paper on holography, which is just that all of these states live in a multiplet whose highest spin is that of the graviton spin 2, and that is a small multiplet, a BPS multiplet of the theory, and so the supersymmetry determines the dimensions completely. Okay. But there are other examples of the duality with less symmetry, where the supergravity states have dimensions that depend on the coupling. They change, but they remain of order 1. Sorry? We're going to talk about examples with less symmetry as we go along. So orbifolds, as Tom mentioned, have 2, 1, or 0 supersymmetries. And so they might actually, to leading order, actually that's not necessarily a good example because they, to leading order in 1 over n, they actually inherit the dimensions of the original states. But things like the conifold would have intrinsically less supersymmetry, and presumably the operators do this. I recall, I'm trying to remember what the interest was, but the interest may actually have been for the purpose of studying some aspects of moduli fixing and inflation. But I remember there's a recent paper by Kashru and others who were talking for some reason about some operator whose strong coupling dimension was 2.79 or some number like that. I'll try to dig out the paper if you're really interested. But I think they were simply interested in the question, what was the lowest dimension unprotected operator, because it entered into various aspects of the phenomenology. And so whatever, that was some operator which, if you followed it back to weak coupling, its dimension must have been some integer. But it ended up at some calculable, probably irrational number when you get to strong coupling. Yeah?
Does that mean that in CFT order 1 operators have no anomalous scaling dimension?
So in the highly supersymmetric example, the anomalous dimensions are 0. In the less supersymmetric, the operators which are not protected, so if their dimension is whatever it was in free theory, their canonical dimension, and normally what you find is something of order g squared. So the operators which, for some operators this doesn't happen because of supersymmetry. For most other operators it happens. And when you get to strong coupling, the statement is that in the ADS5 theory, all the ones that aren't protected end up actually growing in that way. In other theories, in fact, there'll be operators, there are fewer protected operators, and there'll be operators which sort of do something like that. And in particular, so remember what you're doing here is the mass that appears here is the mass as seen in the 5-dimensional, the ADS5 field theory. So you're solving some kind of differential equation, some kind of wave equation on the 5s here, or on some more complicated space whose eigenvalues will determine these masses. And again, as we get to things which are less round than the sphere, the eigenvalues can be they can be irrational numbers, messier numbers, and that's where you get, things that aren't just integers. This is all a prediction of the duality. It's funny because again, this is a very funny field theory. It's a field theory whose coupling is being taken not just to order 1, but to much, much larger than 1. And, if you didn't know anything about ADS-CFT duality and people asked you, what do you think anomalous dimensions do when the coupling gets much larger than 1? Nobody knows. There's no other tool. In fact, I don't know to this day of any analytic argument that reproduces this behavior. It's a prediction of the duality. Presumably, it's something that can be tested numerically eventually. It's the kind of thing a numerical calculation might be particularly good at picking out. Sorry. Yeah?
Doesn't the BMN limit give a class of operators for which you can calculate some
Now, it gives a class of operators.
There's a gauge theory derivation of this.
Right. Good. So you say, I have to think about, I know it's certainly true that in the BMN limit you see stringy operators, but do you get this out of the field theory? How do you do that?
Yes, but I couldn't tell you exactly.
Okay, that's a good, yeah, okay. There was another question, yeah? Tom?
So I'm a little bit lost. So in your conventions, is large delta infrared relevant or?
Large delta is infrared irrelevant.
Okay.
Yeah. Are there people who use the other convention?
There are every possible convention is in the literature, and I'm just trying to find out what yours is.
Yeah, this is dimension in the Wilsonian sense that high dimension operators are irrelevant. Yeah.
Don't the integrability analysis of various functions?
Good. Good. So there are conjectures for what this thing does as an entire function of lambda, using the fact that actually when I listed the symmetries of these two theories, I actually left some out. That is, in the extreme large n limit, if you just look at the leading term, then it appears that on both sides there are higher symmetries which are sort of non-local on the planar surface. And there's a conjectured form for the dimensions of some of these operators which interpolates between this and this. It's never clear to me, though, how much of this is conjecture and how much of it is derived. That whole subject sort of, as with other subjects, often goes by making a guess, checking it, and making a better guess. And I don't think they can yet claim that they can, just from sort of information about the gauge theory, derive that. It's a good question. Yeah.
Another question is, one could have field theories which has protected operators, but with spin more than 2.
Could you? Now, if you did, then, see, if you did, then you would have in the supergravity theory fields of spin greater than 2. And you would need some low energy effective Lagrangian that describes those. And we don't know how to do that. Actually, I can think of it. I don't want to go into it now. I can think there might be a way to do this using more complicated versions. But in general, I mean, it will happen in none of the examples that we talk about because, and it's not surprising it doesn't happen because, again, we don't know of any effective field theory that can describe spins greater than 2 in a sensible way. Okay, so again, the metric, so examples always maps to the ng-momentum tensor. So I told you in the hand-waving derivation that the metric, the graviton, maps to two gauge bosons. And this is sort of a realization of that, because one of the terms in here is like F mu lambda, F lambda nu. So there is a sort of a two gauge boson component to the graviton. So I wasn't totally lying to you, but of course there's other terms in the energy momentum tensor. You know, this is these. So that, and beyond that, it's a little bit unclear to interpret this as a wave function, because this is a strongly coupled theory, and these will always mix with states with more particles. But this is what survives from my original hand-waving derivation, that there's a piece of the metric tensor that maps to something, and where in particular the two polarization indices of the graviton come from the polarization indices of the gauge boson. So I wasn't totally waving my hands. Also, let's see, there's the dilaton, which maps to the gauge kinetic term. So it also is built sort of out of two this was a question they had yesterday, two gauge bosons, but in a spin zero state. There's the Ramon scalar, which maps to the topological density. Actually, sorry, those should be contracted. So this is obviously this is general to any conformal field theory. This is special to the theory we're talking about. Oops, that is these particular fields and operators. Also on the general side, if you have conserved currents in the CFT, you will have a gauge field in the bulk. And in this particular example of ADS5, since the SO6 we have in the CFT an SO6 symmetry, and indeed you can see this global symmetry of the CFT being promoted in the bulk to a local symmetry, because you now have the Kaluza-Klein mechanism. You have the rotational symmetry of the 5-sphere, and so when you look at this from the point of view of the 5-dimensional ADS5 theory, that gives rise to SO6 and SO6 gauge group. And certainly in the applications to condensed matter, you're usually interested. You're interested in the properties of this, and usually the properties of one or more conserved currents. Now,
Do you feel like you derived this, or you just made this up?
I read it in Ed's paper. Sorry, that's a bad joke. But, so where did I get this from? So first of all, counting of dimensions. So a long time ago, good. So a long time ago, before people knew that supergravity was dual to string theory, supergravity people calculated the full spectrum of the harmonics on for the ADS5 cross S5 compactification, and worked out what the m squareds were for all of these things. And you have their masses squared, and you have their symmetries, and it's not hard then to pair those up with the operators. So in particular, they found that this is massless and this is massless, which means they're dual to dimension 4 operators. So there's not a lot of freedom in pairing things up. Now actually, one of the references I gave in my notes was Eric Doker's review. Eric is much more detail-oriented than I am, and gives a long table of the whole dictionary with the SO6 symmetries and so on tabulated, dimensions tabulated. So yeah, and again, just the symmetries and dimensions are pretty much enough to do the matching. Actually, I can tell you that there's another way to do this. I don't know if it always works, but so when we decoupled, when we did the Brainy derivation, we took the Lagrangian limit. We threw away the gravitons. because they were decoupling on both sides. But now we can work a little bit harder and on both sides keep track of the leading coupling to the gravitons. And if you do that on the d-brane side, you find that an incoming graviton couples to this operator in the d-brane theory. And if you do that on the other side, the graviton is just the gravit couples to the. So in fact, the way that Gubser, Klebanov, and Polyakov thought about the dictionary was really in that way, by actually keeping track of the coupling to the outer fields in some sense as you take the low energy limit. And so that's another way to think about pieces, at least pieces of the dictionary.
Well, for example, the dilaton.
Yes.
It's easy to see that it's the Lagrangian because the gauge coupling appears in front of the Lagrangian. You already have the gauge coupling.
Very good, very good. So you're saying what I just told you about Gubser and Klebanov and Polyakov was that already we know the d-brane action has, you say, e to the minus phi trace f squared, and then over in the Ramon sector, there's plus c trace f wedge f. Right. So if you keep track of, again, how the original d-branes interact with incoming dilatons and Ramon fields, so at least for these pieces, yes, I'm not sure. Does this work for all of, yeah. So for these low energy pieces of the dictionary, that's certainly another way to think about it. Yeah.
We could get modes by dimensional reduction of the five-form flux as well.
Well, the five-form flux, you got to be, actually, the five-form, let me come back to that in 1 second. The five-form flux, I'll come back to that in 1 second. Yeah, yeah. So, but then there's bunches more operators. There's traces of, any number of these scalars. Now, there's a natural, again, so this is something which now, and let's make this traceless and symmetric on its SO6 indices. Then it transforms like a spherical harmonic, and in fact, when you match the supergravity modes to the operator dimensions, it has the right symmetries and dimensions to correspond to some shape deformation of the 5-sphere. You just asked about the 5-form flux, and there's a lot of mixing because there's a background to the 5-form flux. The 5-form perturbation will mix with the metric perturbation, and so actually, I believe it's correct to say that these modes are mixtures of the shape modes of the 5-sphere with modes of the 5 flux. But anyway, you've got all of those, and the simplest example of so these are all protected. They're all things whose operators whose dimensions don't get renormalized. The simplest thing, the simplest non-traceless thing. This doesn't map to anything in supergravity, and when you calculate its one-loop anomalous dimension, it's not 0. And so it's the simplest non-protected thing you can write down. And indeed, its dimension is supposed to scale as lambda to the 1/4. And the people who work on this integrability, for the longest time, they were really best at talking about traces of operators that were very, very long, so they didn't have to worry about wrapping around the trace in some sense. And they've recently learned how to think about these wrapping interactions. They can talk about short operators. And again, there's an ansatz at least. I'm not sure if it's more than that. There's a conjecture for how the entire functional dependence of this dimension from weak coupling up to strong. Also, of course, we can shove in a bunch of scalars into any of these other operators, and they become the Kaluza-Klein modes, the S5 harmonics of these corresponding fields. I think there's one more. I'm going to use I'm going to use various pieces of this dictionary later on. I think there's one more I want to mention. This.
Is there any restriction of identifying the string states?
So, in some sense, roughly speaking, the only thing you can do is to take, say, I think the following is true, but not much has been done. Take, say, a given set of quantum numbers, like the SO6 singlets, and list all of the states at weak coupling, list all the states at strong coupling, and since levels won't cross in general because of states mixing when not allowed by symmetry, all you can say is that each of these will eventually map to each of these. But it's kind of a messy thing, protected anyway, and so they'll mix a lot as you. Not sure what one that is really. Well, I mean.
For example, the Konishi, which is like very small dimensional weak coupling.
Yeah, but I mean, so I mean, could Konishi and some other operator cross? Wow. Superpotential perturbations giving masses, for example, to the superfields, and these map to the lowest harmonic of the. They mix the Ramon and Nouveau-Schwarz free-form fluxes, and then of course higher harmonics come when you throw in more scalars. And again, the dimensions match up, dimension 3, I guess, here, and so on, and the symmetries. So, I gave you that homework number 1, which was to find a reason why this duality couldn't be true. And anybody who answered there's just not enough states in the gauge theory to match to the string theory, you get a point. Because it's a natural answer. In fact, this argument more or less appears in Roger Penrose's Road to Reality, I think it is, where he answers problem number 1. And his specific answer has to do with the fact that, as we've said, the phi sphere is large. And so it's not merely that it's a 5-dimensional theory dual to a 4-dimensional theory. It's a 10-dimensional theory dual to a 4-dimensional theory. And then the question is, where do you get all of those, extra states from the 10-dimensional theory? Well, they come from this. And where they really come from is the fact that you have large N matrices. The secret, of course, is that the field theory has a lot of degrees of freedom because N is large. And where that shows up here is that if N were small, well, once we get to N operators in the trace, since I can write the trace in terms of eigenvalues and there's only N eigenvalues, once I get to more operators, then the trace ceases to be independent. And so it's secretly large N that's allowing me to write down the high harmonics on the sphere. Now, it's another interesting comment on the non-perturbative behavior in N, which is if N is finite, then past a certain point, these traces cease to be independent operators. And so it seems like there's an upper limit to the harmonic, the momentum along the 5-sphere. And this was nicely explained by McGreevy, Susskind, and Tumbas, I think, in terms of the supergravity states blowing up into giant gravitons that wouldn't fit in S5 anymore. So it's another nice example of the non-perturbative behavior in N. Now, as Tom was just mentioning, a black hole state you say might be a disordered trace of order n squared fields? Is that the sort of thing? Yeah.
What they said in
right.
the paper, this is
right.
this is states that have energy of order n squared.
Right.
In the G equals 0 line.
Okay. It might be single. It might be products of many traces. I don't know. Also, my statement. Actually, I'm suddenly confused. If the trace is not symmetrized, maybe there's more. And I'm not okay. Well, we can get more on that story from Hong when he gets here. Okay. So I'm just about out of time, and I'll say one more thing very briefly. I think that many later speakers will talk about what happens when you heat things up. So this will be the only commentary I make about temperature. But of course, in addition to trying to count explicit states on a 1-by-1 basis like this, you can count all of the states by forming the partition function, the thermal partition function, and say calculating the entropy as a function of temperature. And there's this famous factor of 3/4 that in the free field theory, if I copy this down correctly, this is 2 pi squared over 3 n squared t cubed and pi squared over 2 n squared t cubed. So this is free CFT, just counting up the thermal entropy of free fields. There's n squared of them. And this is from when you heat up a gravitational system, it's from the black brane horizon area. And the agreement to form is satisfying. It probably couldn't have failed given other things, but it's still satisfying. In particular, this is saying that the gravitational theory really is behaving like a 3+1 dimensional conformal field theory. The Tufts scaling is kind of built in. What's not so the n squared. What's not so obvious here, what's a surprise, and it really is that as you increase the coupling in the so when we talked about anomalous dimensions, we had these two possible behaviors. I guess I've erased them now. But as you increase G, the anomalous dimension can get bigger and then maybe turn over, or get bigger and then keep getting bigger. And we don't really have a deep understanding from the field theory of why one or the other happens. And in this case, too, empirically, what this is saying is that as you turn up the coupling, the interactions tend to reduce the entropy. They tend to reduce the density of states, pushing states to higher energy. But in fact, for most states, this doesn't go very far, and you end up with this kind of behavior. Remember, most states from this point of view is not just these single particle states we've been counting. It's very dense. It's another branch of the spectrum. It's states which are very dense in the CFT, and even the color singlets lose their identity. You're in the deconfined phase in a sense. Anyway, this is the factor of 3/4. The curious fact that when you heat up the system, its entropy is very similar to its free entropy. And this is neither a success nor a failure of the duality. It's just an observation, because I think we don't really have any independent way to think about the fact that this is what happens. But anyway, but in some sense there is this gross counting of the states on both sides, and this is really counting all the states. Black holes have huge entropy, and even when you count all the states, you have just about as many states in the free field theory. Okay, so I didn't get as far as I thought I would today. I guess tomorrow I'm going to start to calculate some correlation functions, just a few to illustrate the operation of the dictionary. Yes?
Substantiate that dipole picture in this operator?
So
How do I see that Z is the scale which corresponds to this?
If you act with a local operator in a control field theory, and then watch the system evolve, there's an argument, I think, due to Coleman, and I forget all the assumptions, but just basically the symmetry plus conservation of the energy momentum tensor tells you that if you ask where the energy is at time t later, it's in a ring of radius t around where the original operator acted. And so I have to think about the precise statement of that. What that's saying is in the CFT, whatever it was you created, well, at least the energy density has moved out. All of the degrees of freedom, at least in terms of their energy density, live on a circle of radius z. And in the bulk, using this dictionary, at time 0, you created some field. You created some field on the boundary, and it has now moved it has moved a distance z into the interior. So you can actually track, I think, expectation values. So you can actually set, you can. I've tried to use this, for that problem of how you sort. This is the rough argument, though. After a time t, on one side of duality, there's no question the size of the state has grown at the speed of light. On the other side, it's propagated into the interior, the matching distance. Yeah. Question?
So is this n squared dependence of the entropy? Is it due to this factorization in the Lassian?
Well, well, Tuft counting tells you that. I'm trying to think of how to relate it to the diagrammatics, but tough scaling tells you that it's n squared t cubed times some function of lambda. And I mean, it's this doesn't always happen in large N theories, by the way. In confining, this theory is conformal. In confining large N theories, since at low temperature you don't see all degrees of freedom, you just have the singlets, you get a phase transition to an n to the 0 behavior. So it's not universal to all large N theories. But here it's really just, I think, the fact that you're in the same phase as the free theory, and so all you can get is functions of lambda. That's the,
Presumably you know that it's stats and put it to a constant when lambda goes to infinity.
why? Why couldn't it go as 1 over lambda to the fourth?
Oh, whatever lambda to the fourth.
Yeah, 1 to the 1/4. What if the typical state did the same thing as a stringy state and got heavier in this way? Then all of your spectrum is shifting up as you increase the coupling, and the entropy would be falling. That's a logical possibility, and it doesn't happen here, but it happens in other places.
So there are examples where this quantity goes to 0.
There are so for the M2 brane theory, this is n to the 3/2, which has no obvious interpretation. But in fact, you can get that n to the 3/2. That has to come out, as I'll talk about later on, sort of a non-tough scaling limit of a theory where you started with n squared. So there are cases where the entropy really is qualitatively affected by interactions. And again, no clear understanding of when it is, when it isn't, from the field theory point of view. Again, something which the Monte Carlo people might eventually be able to at least confirm, if not explain.
Would S over, I'm totally agreeing, would S over eta be equal to 0? Is that a physical?
S over eta. Well, sorry, I haven't talked about eta yet, but whatever S does, I presume eta will do something similar. I haven't.
Would it be a physically sensible result to get 0 on the right-hand side?
Wait, eta is the viscosity?
I mean, the quantity that you wrote there.
Oh, of volume. S over V. S over V. S over V. S over V. Well, I mean, when lambda's strictly good question. We do actually have some information about what happens when lambda is order n squared. Because when lambda is order n squared, when lambda gets very, very strong, the supergravity picture breaks down, and we get into the dual gauge theory picture. Does that mean the entropy goes up again? It must. Yeah, because yeah. So we don't usually talk about this much. It doesn't come up much, but you know the n equals 4 theory has two strong coupling duals. There's the one where you take g squared n to I'm going to get this wrong. So there's g squared n, but then there's the S dual theory, the S dual gauge theory, where the relevant thing is n over g squared. So there's a very weakly coupled regime, which is the n equals 4 theory. There's the ADS theory, where this is of order 1. There's then another transition where this is of order 1, and there is the magnetic, call it, n equals 4 theory. So actually, we do have some information about what happens when lambda gets so large. So this is n squared over lambda. So when lambda gets so large that it's of order n squared, then we know actually what this function does again. But if we first take n squared to infinity and then take lambda to infinity, we don't know anything about what that function does, and it should go to 0. Yeah?
I don't actually think that makes sense.
Which?
What you just said.
Really?
Being of order n squared. So
Yeah.
the lambda is something that's defined order by order in the large n expansion, which is divergent expansion.
Wait, sorry. You mean in the field theory?
Yeah.
Well, but G Yang Mills squared is defined, isn't? I mean,
G angles is defined, but the idea of talking about lambda is something that only makes sense in the large n approximation, and the large n expansion is divergent. So lambda of order n squared
yeah.
is a place where the 1 over n approximation is broken.
Sure.
You can't really talk about lambda. You have to talk about, the lambda.
Well, I can talk about. I mean, I guess I'm.
Dual to 1 over g squared.
There's this. Well, I mean, I can talk, but there's this. I mean, this is obviously a non-Tuftian statement, and yes, we usually talk about lambda in a context where it's what we're holding fixed when n varies. But there's two parameters, and I can call them. All I'm saying is there's two parameters. I can call them g squared and n or lambda and n.
I think if you think in this way, you can get yourself really confused by trying to impose that g squared goes to 1 over g squared duality on the 1 over n expansion.
No. Okay, good. So it's good. So what Tom is, I mean, the key point, this duality in the gauge theories at the extreme ends of the coupling range is not visible, certainly order by order, in the bulk theory. It's a strongly non-perturbative statement about the quantum gravity.
You just have to do it at finite n.
Pardon?
You have to work at finite
Yeah, you have to work at finite. I mean, in some sense, you have to work at finite n to even make these statements. That's right. Right. But so in the bulk, you're interchanging fundamental strings and D strings, and that's exchanging the electromagnetic in the gauge theories. Okay, very good.